Dear students, Assalamu alaikum. In the previous lecture, we were studying classical theory of Raman scattering. Now we continue with the same topic, classical theory of Raman scattering. In the previous lecture, we have discussed that for a molecule to be Raman active, for a molecule to be Raman active, it must have a change in its polarizability. It must have a change in its polarizability. We had discussed the case of hydrogen, in which the electromagnetic radiations, they fall on the molecule parallel to the axis, or they interact with the molecule perpendicular to the axis. Now here in this case, alpha parallel, and in this case the polarizability is represented by alpha perpendicular. We had already discussed that polarizability along the axis, along the bond axis, is very high, and polarizability perpendicular to the axis is low. It means that alpha parallel is greater than alpha perpendicular. The polarizability of molecules can be represented by a diagram which is known as polarizability ellipsoid. Polarizability ellipsoid. We know that in this case, in the case of hydrogen, the polarizability along the bond axis is very high. They are easily polarizable, and polarizability perpendicular to the bond axis is very low. Now, if the polarizability, now we can represent it by the polarizability diagram, which will be as follows. This axis, it represents the polarizability along the bond axis, and this line represents the polarizability along perpendicular to the bond axis. Generally, if the polarizability is high, this bond axis will be small, and if the polarizability is low, the bond axis will be a larger one. Now, the smaller axis in this diagram is known as polarizability diagram, and in this diagram, the smaller axis is called the minor axis, and it represents high polarizability, and the larger axis is called the major axis, and it represents smaller polarizability. Now the distance from the central point toward the length of the axis from the central point is governed by the relation I is the length of the distance or displacement from the central point of an axis, whether it is along minor axis or along major axis, is inversely proportional to square root of polarizability. And this mathematical expression clearly shows that if the polarizability increases, the length of the axis will decrease, and if the polarizability increases, length of the axis will, if the polarizability decreases, length of the axis will increase. Now there are, on the basis of polarizability, molecules may be of two types. one more thing, if a molecule has a high, is easily polarizable, then it will be represented by a small ellipsoid. And if a molecule is less polarizable, then it will be represented by a big ellipsoid. A big ellipsoid represents low polarizability, and a small ellipsoid represents high polarizability. Now, on the basis of polarizability, molecules may be divided into two types. Number one, first type is known as soft molecules, and second type are known as hard molecules. Molecules can be divided into two classes on the basis of polarizability: soft molecules and hard molecules. Soft molecules are those molecules which can be easily polarized. Examples of such molecules are the compounds which contain pi electrons. Compounds which contain pi electrons are molecules which contain pi electrons. Pi electrons are loosely bonded, hence they can be easily distorted. For example, in case of benzene, we have delocalized pi electrons. Benzene is the example of soft molecules which have pi electrons, which is a conjugated system containing delocalized pi electrons. Now, these pi electrons can be easily distorted by application of external oscillating electric field or electromagnetic radiations. Now, the second type of molecules are those molecules which are called hard molecules. These are the molecules in which the electronic clouds cannot be easily distorted. Hard molecules are those molecules in which the electronic cloud cannot be easily distorted. These are the examples of such molecules are those molecules which contain sigma bonds. We know that sigma bond is a rigid bond. We are using this term rigid because the electronic cloud is a shared electron pair between two atoms is tightly bound, and it cannot be easily distorted. It is less polarizable. Example is water molecule. Sigma bond is very much stronger, and the electrons cannot be easily distorted by application of external oscillating electric field or by electromagnetic radiations. In case of benzene, which is easily polarizable, it will be represented by a small ellipsoid. And in case of water, as a polarizability, it is difficult to polarize, therefore it will be represented by a larger ellipsoid. The magnitude of polarizability in benzene is very high, and the magnitude of polarizability in water is low. Now we come to mathematical portion of the classical theory of Raman scattering. Mathematical description. We had already discussed that if we have a molecule which may be polar or non-polar, and it is placed in an electric field of strength E. Let us suppose we have this electric field of strength E. Consider a molecule which is placed in an applied electric field in this applied electric field, a dipole moment, polarity will be created in the molecule. Polarity will be created in the molecule, and there will be an induced dipole moment mu created in the molecule. This induced dipole moment directly depends upon the electric field, strength of the electric field. Mathematically, we can write mu is equal to alpha E, where alpha, mu is the applied electric field and alpha is polarizability. E is oscillating electric field. And mu is dipole moment. Equation number 1. Now the oscillating electric field is given by electric field strength is given by E is equal to E naught into sine 2 pi nu t, where nu is the frequency of electromagnetic radiations. For example, laser radiations are used in case of Raman spectroscopy. Therefore, we may consider it as the frequency of electromagnetic radiation. The polarizability alpha is given by the relation alpha naught plus d alpha by dq into q naught sine 2 pi nu vibration into t, equation number 3, where alpha is the change in polarizability which is caused by oscillating electric field, or which is caused due to vibration. d alpha by dq is the rate of change of polarizability with vibration. Alpha naught is the equilibrium polarizability. When the molecule was present at its equilibrium position, it was also polarizable, and it is that polarizability which was present at equilibrium. d alpha by dq is the change in polarizability with vibration. Q naught is the equilibrium vibration, equilibrium molecular vibration. And new vibration is the inherent vibrational frequency. Inherent vibrational frequency means the frequency which was possessed originally by the molecules. Now putting these two values into equation 1, let us rub it. Now we had the equation, main equation was mu is equal to alpha into E, equation 1. Putting the value of E and alpha from equation 2 and 3 into equation 1. Putting the values of E and alpha from equation 2 and 3, equation 2 and equation 3 into equation 1 respectively.